try to deal with any questions you might have. And again, as usual, if you have any questions, just raise your hand, inshallah we'll help you. Today I'm very happy to let you know that Dr. Khaldoon Rumeh is with us. He's attending a few of the lectures. He's one of the faculty at King Faisal Specialist Hospital. Inshallah, he would like to contribute to this block, so maybe next year he will be participating in the teaching with us. Welcome, Dr. Khaldoon. Today, we will talk about the body fluid compartments, and as you know, we covered that in the foundation block. What we are going to be talking about is the extracellular or intracellular fluid compartment. Now, this might not sound to you as if we're talking about the kidney per se, but we are, because the body fluids, regulation of body fluids is one of the major functions of the kidney. Okay, but we're going to review this before we get any further. What do we want to know about the body fluid compartments? Well, we want to know the constituents of the different compartments. And again, remember, these are mainly the intra or extracellular fluid compartment. How do we measure these different compartments? Because remember, in medicine, we like to get numbers for specific things. That's how we usually diagnose problems. If we know what the normal level is, if it is changed, that gives us an idea of what the problems are. So we want to see how we can measure these compartments. How are they regulated? And what determines how much I'm going to have in the intracellular fluid compartment versus extracellular fluid compartments. Of course, I'm talking about the volumes. We're going to talk about the basic principles that regulate osmosis, and we will define osmotic pressure, and we will find out, why do we need to know anything about, osmotic pressure. Osmotic equilibrium between the intra and extracellular fluid compartment, as well as the volumes and osmolalities of the intra and extracellular fluid compartments under normal condition, as well as during disease states. Then at the end, we will talk about some of the abnormalities that can occur in these compartments. Remember, we're talking about volume and constituents. So what are the abnormalities that can occur? Either you have an increase in volume or a decrease in volume. Usually, when we have an increase in volume, we usually call that edema. Some of the constituents might change. You know what's the concentration of sodium in our extracellular fluid compartment? It's about 140 milliequivalents per liter. So if it goes down, we call that hyponatremia. If it goes up, we call that hypernatremia. And of course, that can have an effect on your whole body, because it can affect the action potential as well as any other functions of the cells. Now, do you still remember what is the osmolality of the intra and extracellular fluid compartments? First, are they equal? Are the osmolalities the same in the intra and extracellular fluid compartment?
No.
Yes. Who said no? Who said yes? Okay, 3 people said yes. Nobody said no? You said no? Changed your mind?
I said
okay, the osmolality is equal, and the reason for that is because the cell membrane is permeable to water. So osmosis is the movement of water from high concentration of water to low concentration of water. So if I have a membrane that's permeable to water, water will continue to move until the concentration of water is equal on both sides. And when the concentration of water is equal on both sides, that means the osmolality is equal.
Osmolality or the rating?
Osmolality or osmolality?
Yes.
Anything you want.
Aren't they different?
They are the same. The difference is 1%. We will define that in a minute. Okay. Balance of fluid intake and output. Now remember, I don't know how long you're going to live, but you've been around for what, 19 years or something like that? Probably you will not have 2 days in your life where you have the same fluid intake as any other day. Okay, remember, if you remember every day in your life, you probably don't, but you will never drink or eat the same amount on any day as compared to the other days. So what does that tell us? That tells us that our intake of fluid varies every day. However, طبعا it can be regulated by few things, and we will deal with that before the end of the block. But your intake varies every day. Ya Shabab, and then, do you have any questions? No, I can hear you from here. If you have a question, just raise your hand. Okay, so the intake varies, but your body weight doesn't vary, right? I mean, from day to day, it's probably the same. What that tells us is that the amount that your intake is really equal to your output. So now the kidney, every single day, it has to look at this intake that you took, which is different than any other intake you took during any other day of your life, and adjust the urine flow rate in such a way whereby the intake is equal to the output. So this is one of the main functions of the kidney. Now your average person consumes about 2.1 liters of fluid per day. That's not only fluid you drink, that's in the food or any other thing that you consume. And our own body synthesizes about 200 milliliters of water per day. That's as a result of oxidation of carbohydrates. One of the end products of these reactions is water. So we make about 200 milliliters of water. I consume about 2100 milliliters of water. So we have 2300 milliliters of water that I have as an intake each day. Now, trust me, the amount that I lose each day is exactly the same. And how does that happen? Well, we have about 700 milliliters that we lose each day. We call that the insensible loss. This is fluid that you probably don't notice, but you lose some fluid by evaporation from your skin. Remember, your skin is large, and so we were close, but still you have some fluid that evaporates. This is totally different than sweating. This is just evaporation. Not only that, but you also have about some amount of fluid that you lose because we are breathing all day. Remember our respiratory passageways, they're in our body, and our body has 60% water, but you don't have a lot of water vapor in the environment. So as we breathe all day and all night, we are losing a certain amount of water also through our respiratory passageways. This is called insensible loss. Okay, so this is, we call that the insensible loss, and it's not very well controlled. Okay, you cannot say, oh, no, today I'm going to lose only 350 milliliters by evaporation, or 350 milliliters only through my respiratory passageways. The reality is we lose about 700 milliliters per day through these two places, and in fact, we lose about 350 from our respiratory passageways and 350 from the skin, so it's kind of 50-50. And then we lose about 100 milliliters per day by sweating. Remember, this is under normal circumstances. You might not feel that you are sweating, but you do have sweat glands, and even when you're not doing much, like today, you're still losing about 100 milliliters per day of sweat. Now, this can change. Remember that if you go out and exercise, you will lose a lot more. So in an unacclimatized person, you can lose as much as 1 liter per hour through sweating. Now, sweating is controlled. Or if you are a construction worker and you're working outside 8 hours a day, you're acclimatized, you probably will be losing about 2 to 3 liters per hour of sweat. So remember, we tell these people to drink a lot during the day in order for them not to get dehydrated. But for our purposes, we lose about 100 milliliters per day by sweat. We lose about 100 milliliter in the feces. So if you add all this together, 700, 100 and 100, that's 900. 900, if you subtract 2300, reduce that by 900, how much do you get? 1400, and this is the amount of urine, your average urine flow per day. So now, how does the kidney regulate our body fluids? Now, let's say I went out and started running, and I'm losing a lot of fluid by sweating, what is going to happen to the urine flow rate? Is it going to go up or down?
Down.
It will go down if I'm not consuming a lot of fluid. But remember, if I'm going out and running, I'm probably drinking more than 2,300 milliliters per day. Okay? So if you look at this, the insensible loss, it's very hard to control that. It's very hard to control the 100 milliliters that I lose in sweat. It's very hard to control the 100 milliliter per day that I lose in the feces. So therefore, this is the one that I control usually. And the kidney regulates that almost to perfection, whereby your intake and output will be equal for that particular day. So from now on, we're not going to count any of those, but you know they exist. I'm not going to speak about this anymore, and this is the renal block. Now I'll say it, if you drink 2 liters per day, you will excrete 2 liters per day in the urine. But you know, there are also extrarenal losses, so keep that in mind. But we're doing that, and this is the amount that we can control. This is the renal block, so we want to know how the kidney does that. Okay, so the extracellular fluid compartment is about 14 liters in your average person, and it's divided really, the fluid in it is distributed in 2 compartments. One is the plasma, which is intravascular, and the interstitial fluid compartment. And what's between the plasma and the interstitial fluid compartment? What kind of membrane do we have? Capillary membrane. Is the capillary membrane permeable to everything?
No.
Everything except blood cells
Proteins.
and large plasma proteins. Everything else is fine. Sodium, glucose, every water, it can go through in both directions. Okay? What about between the intracellular, which is about double the amount? See, this whole thing is 14. Intracellular fluid compartment is 28 liters, double. What's between the intracellular and the extracellular fluid compartment?
Cell membrane.
Cell membrane. Is that permeable to anything?
No.
No, except water. Okay, so that's how you need to understand how both compartments, what kind of volumes you're going to have in each one of them.
But the capillary membrane is not permeable to albumins.
Yes, that's large plasma protein. Yeah, it's not permeable to plasma proteins. Except, if there's something wrong with it, but we're talking about normal circumstances. Okay, well now, in addition to the intra or extracellular fluid compartments, we have another compartment called transcellular fluid compartment. This is about 1 to 2 liters in volume. We don't talk about it a lot, but you need to know it exists. This usually contains extracellular fluid. The constituents are similar to the extracellular fluid compartment, but you might have little variation. What are the components of this transcellular fluid compartment? These are the synovial fluid. This is the fluid in the joints. The peritoneal fluid, pericardial fluid, intraocular in your eyes, as well as digestive fluid and the cerebrospinal fluid. So this whole thing is about 2 liters, 1 to 2 liters. It is a little bit separate, but it is almost a part of the extracellular fluid. It has similar components. Now, what do I have in the extracellular fluid compartments? I have a lot of sodium, a lot of chloride, and a lot of bicarbonate. What do I have in the intracellular fluid compartment? A lot of potassium, a lot of magnesium, a lot of proteins, as well as a lot of phosphate. Now, so you notice now the constituents are different, but the osmolality is the same. Okay? So we always talk about the extracellular fluid compartment. The extracellular fluid compartment has a lot of sodium, chloride, as well as bicarbonate. So therefore, we find out, from experiments, that about 94% of the osmolality that we have in the extracellular fluid compartment is caused by sodium chloride and sodium bicarbonate under normal circumstances. So really, if I take a blood sample or a plasma sample from somebody, and I have an idea how much sodium does this person have in their extracellular fluid compartment, I probably can predict what's the osmolality going to be. And we will see how we do that in a minute. Now, we have this empirical formula. If I know the sodium concentration in the plasma, I multiply this by 2.1 and it will give me the plasma osmolality. Now you might say, why am I doing this? Do you think we can measure osmolality directly? Have you ever heard of anything that can measure the osmolality directly? No? Let's say I tell you that there is something that can measure the osmolality, a machine. What do you think its name would be? Osmometer, yes, that's right, we said that. Okay, we do have something called osmometer and you can measure the osmolality, except I used to do that a lot in my lab and the technicians hated to do that because it's not easy to use the machine and it requires a lot of patience, you know. So people don't like that. Not only that, but if you're practicing medicine in a small town somewhere, they're not going to have an osmometer. But they will have a machine to measure sodium in the plasma. Okay, so it's a lot easier to measure sodium under in small towns anywhere, but they're not going to have an osmometer. So if you measure sodium and you multiply that in the plasma, you multiply that by 2.1, you will get the osmolality of the plasma. If the sodium concentration was 142 milliequivalents per liter, which is the normal value, you multiply this by 2.1, you get an osmolality of the plasma of about 300 milliosmoles per liter. Yes?
To multiply by 2.1 because of the dissociation of sodium chloride?
Because of what?
Dissociation of sodium
No, because somebody went to the lab and he changed concentration of sodium in the plasma. He made it 142, then he measured the osmolality. Then he made it 140, he measured the osmolality. He changed it within the normal values, and they found out that the constant that you need to multiply the concentration of sodium with to get the osmolality is 2.1. This is empirical. Empirical, usually we find that out by experiments. Bicarbonate. We have phospholipids, we have cholesterol, we have glucose, of course, we have creatinine. Remember, this is a number that we want to pay attention to because this is the renal block. We'll talk about that later. But there are other things in the plasma other than sodium chloride, sodium bicarbonate. But the osmolarity is determined by sodium chloride, sodium bicarbonate. Now we said the cell membrane is highly permeable to water, right? It doesn't allow anything else to go across except sodium, potassium. They can, I can move sodium to the outside, potassium to the inside, but that requires energy. This is transport. It's not just, going by itself. The cell membrane is not permeable to either sodium or potassium, but with active transport, you can move sodium to the outside of the cell and potassium to the inside of the cell. Of course, that requires ATP, and it is an example of primary active transport. Okay, well, I'll let Mr. Weil here take attendance. These different compartments, yes, sir.
Sir, you said like the total water loss.
Okay, guys, let me hear the question.
Net water exchange is 2,300 milliliters, right?
Net water what?
Net water exchange, water loss and water gain is 2,300 milliliters, right?
It's 2.3 liters.
2,300 milliliters. So, but the volume of the blood itself is about 5 liters. So can you explain?
Well, the blood has nothing to do with it.
No, but I'm just saying the total body, like the fluid amount in the body.
Yeah, so what's the problem? I'm drinking 2.3 liters, we're excreting 2.3 liters.
So we have the set amount of fluid that never exchanges in the body.
The water that, one molecule of water that I drink doesn't mean necessarily the one that I just lost. Okay. So there is exchange, but it's not the same water.
Doctor.
That's,
Doctor.
you understand what I'm saying? Okay. Now these compartments, again, as researchers, as physicians, we like to get numbers. We told you that. You have a question?
I have a question regarding the osmometer.
We will get to the osmolality. We haven't got it there yet. So wait till we get there. If you still have a question, inshallah, we'll help you. Okay, we just told you that the intracellular fluid compartment is 28 liters. The extracellular is 14. The total body water is 42 liters. Your blood volume is 5 liters. Your plasma volume is 3 liters. So how did we measure that? Well, there are methods to measure all these. Well, I calculate them in some cases. And this method, mainly the one that we use very often, is called the indicator dilution principle. And this works on the preservation of mass principle. Now I have here a syringe with an indicator in it. I know how much I have here, volume, and if you have seen a syringe, there is numbers on it, so you can tell how much fluid you have in there or how much volume you have in there. So I know the volume of this indicator, and I know the concentration of this indicator in the syringe. So the mass of the indicator is really equal to the volume times the concentration. Okay? Well, now this volume, when I put it in this container, the mass is still the same. See, this mass here, it was in the syringe, but when I put it in the container, the mass is still the same. So therefore, the mass of indicator A is equal to the mass in this container now, which is called B. It's not the syringe. The only difference is the concentration was very high here, but it's lower here, and this container is bigger than the syringe. Okay? So what am I saying? The volume of A times the concentration of A, and both of them I can measure, right? Is equal to the concentration of B, which I can measure, times the volume of B, which I do not know. So now I have 4 numbers. I know 3 of them. So therefore I can determine the 4th number. Because of that, again, this is the conservation of mass principle. So this mass is equal to the indicator mass in the container that's bigger now. Okay, so mass of A is equal mass of B. I have the volume in the syringe, the concentration of the indicator in the syringe, the concentration of the indicator in this container. So therefore I have only the volume missing, and I can calculate that.
But before you inject the volumes and how do you look at the concentration?
I can measure it. Let's say it's glucose. I can measure the concentration of glucose in fluid. I haven't told you yet what the indicator is. Okay, this indicator is not. We are calling it an indicator, but you need to use specific indicators depending upon what volume you're trying to measure. Okay, now what are the requirements that I need to have in an indicator to be able to use it for the measurement of a certain compartment? Well, the indicator must disperse evenly throughout the compartment. And I mentioned the concentration is a lot higher in this corner versus that corner. That doesn't work. It has to disperse evenly in the compartment. It has to disperse only in the compartment that I'm trying to measure. And I cannot infuse it in A, it goes to B. I'm trying to find the volume of A. It doesn't work because I will not be able to account. Then the conservation of mass will not be true anymore. And it should not be metabolized or excreted. And if I put this indicator, let's say it's sugar, I don't want it to become something else. And then if I'm measuring the concentration of sugar and it became something else, then I will have an error in my measurement. So it should disperse evenly in the compartment I'm trying to measure. It should disperse only to the compartment I'm trying to measure, not to other compartments. And it cannot be metabolized or excreted. Now let's look at some examples before we get to looking at some examples for applying this method. Well, we have the compartment volumes as percentage of your body weight. We have this rule. We call it 20-40-60. Some people call it 60-40-20, whatever makes you happy. 20% of your body weight is extracellular fluid volume. 40% of your body weight is the intracellular fluid volume, and total body volume, total fluid volume in your body, in your whole body, is about 60% of your body weight. So again, 60% of your body weight is water. So if you weigh 70 kilograms, you practically have about 42 liters of water. Okay, 42 is even 60% of 70. Now, what are some of the indicators that, remember now, the extracellular fluid compartment is made up of plasma with interstitial fluid, right? The intracellular fluid compartment is all the fluid that we have inside the cells. Now we find out that I can measure blood volume by chromium. Chromium seems to, chromium, if you expose blood cells to chromium, they will tag the red blood cells. So if I take some red blood cells that are tagged with chromium, I know the concentration, how concentrated these blood cells are. Of course, I give them to a person, the same blood type, and then I can measure the concentration of chromium in the blood sample that I take from this person. Then I can apply the indicator principle, indicator dilution principle to determine the blood volume. How do I measure plasma volume? Well, we have a substance called Evans blue. What do you think its color is going to be?
Blue.
Yellow.
No, it's blue. Not very smart. Who said that? Oh, this is blue, and it tags to plasma albumin, well, plasma proteins. Okay, so therefore, if it goes only and tags on albumin, and I know we have a lot of albumin in the plasma, so if I give a certain amount of Evans blue, I know the concentration in the amount that I gave. I take a plasma sample, measure the concentration, and then therefore I can determine the plasma volume using Evans blue. There are other radioactively labeled proteins can be used also to measure plasma volume. What about the extracellular fluid volume? If I give a person an IV infusion of sodium, let's say, a solution of sodium, do you expect any of that sodium to enter the cells?
Yes. A little
Why?
bit.
Why? A
Because
little
the-
bit. Who said a little bit?
Concentration.
And how does it enter the cell if it's a little bit?
Fusion.
Sodium, potassium, ATPase, but that's an extremely small amount. Practically, if I give sodium from outside, it will remain in the extracellular fluid compartment. So if I tag that sodium with radioactive material, then it will stay only in the extracellular fluid compartment. I know the concentration, I know the radioactivity in the amount I gave, I know the amount I gave, and then I measure the radioactivity in the sample that I take from the plasma. This will allow me to determine the extracellular fluid volume. Total body water. Do I know of any substance, if I infuse, it will go everywhere? It will go to the intracellular or extracellular fluid compartment? Water, yes, I know it crosses membranes, both capillary membrane as well as cell membrane. So therefore, if I give radioactive water from outside the body, we don't have radioactive water in our body, so I give some to this person, then I take a sample from anywhere, and I measure the concentration or measure the radioactivity, I can determine the total body water. There are two things I cannot determine directly or measure. One of them is the intracellular fluid volume, because I do not know of any substance that will only go to the intracellular fluid compartment. So therefore, I cannot measure that. I also do not know of any substance that will only go to the interstitial fluid volume. So therefore, these two can be calculated. You cannot measure them directly. How do I calculate them? The intracellular fluid volume, if I know the extracellular fluid volume with total body water, I can subtract total extracellular fluid volume from the total body water. I can measure total body water, I can measure extracellular fluid volume, so therefore I can determine the intracellular fluid volume. Also, if I know the extracellular fluid volume, I know the plasma volume, I can determine the interstitial fluid volume. Yes, sir?
For the sodium, is that like that sodium can actually enter the cell to actually?
Yeah, but that's a very small amount as compared to the amount I give. Yeah, you know, active transport, it doesn't, it moves 3 sodiums, 3. You're not talking, you're talking about a lot more than 3.
يعني في channel خاص في هذا
again, remember in medicine,
الشنب
this
الخاص
is not
فيها
like
قال
math, you know.
لا ما
In medicine, medicine is an art, it's not a perfect science. So all these numbers I'm giving you, there is probably plus or minus 10% easy. You know, so these are the averages or what we see. Okay, well now, let's say I want to determine the blood volume from the plasma volume. We have a formula for that. Blood volume is equal to plasma volume over 1 minus hematocrit. Okay, or of course you can measure blood volume directly by, chromium or radioactive chromium. Okay, so these are the methods we use to quantify these compartments. Now, what about osmosis? You know, remember, water can cross any membrane we have in the body. The two membranes that we're interested in are the capillary membrane as well as the cell membrane. Water can go everywhere, and it goes everywhere by diffusion. However, we call diffusion of water osmosis. And how do you define osmosis? It's the net diffusion of water across a selectively permeable membrane, and permeable to water. And of course, how does it move? What are the principles that regulate osmosis? Water moves from high concentration of water to low concentration of water. It's the same like diffusion of any other substance. Diffusion is always from high concentration to low concentration. Remember, there is movement of water on both sides. However, the net amount is really mainly determined by the movement of water from high concentration of water to low concentration of water. The osmolarity of the body fluid compartments is the same, because water can cross cell membranes, it can cross capillary membranes. So the osmolarity in the intracellular fluid or extracellular fluid is always the same at equilibrium. Inshallah, we will give some examples towards the end of the next lecture tomorrow, whereby we can infuse fluids in a person and we can determine what's the new level of intracellular or extracellular fluid compartment in these patients. Now, what determines the relative amount of extracellular fluid distribution between the plasma and the interstitial space? Does anybody know the answer to this question? Remember, the extracellular fluid compartment, it's composed of plasma volume with interstitial fluid volume. What determines, well, I'm going to have 3 liters of plasma or 11 liters of interstitial fluid?
Salt.
Starling forces. Remember, the membrane I have between plasma and the interstitium is the capillary membrane. We said the capillary membrane is permeable to everything except blood cells, large plasma proteins. So therefore, what determines the relative amount of extracellular fluid distribution between the plasma and the interstitium is Starling forces. And you remember these Starling forces, we have 4 of them, 2 hydrostatic pressure forces and 2 colloidal osmotic pressure forces. And the net pressure, the net filtration pressure is only 0.3 millimeters of mercury, favoring movement of fluid from the vasculature into the interstitium. If you determine this pressure and Kf, this is the filtration coefficient, you multiply them by each other's, you multiply that by 1440 minutes that we have each 24 hours, you will get a number which is about 2 liters of fluid that move from my vasculature to my interstitium over a period of 24 hours. And a lot of that fluid is brought back to my vascular system by the lymphatics. So we don't lose, this fluid is not lost. It kind of moves into the interstitium, comes back to my blood. What determines the distribution of fluid between intracellular and extracellular fluid compartments? Water movement, right? I know these membranes are permeable to water. So how is water going to move from high concentration of water to low concentration of water or not? Yes, and let's say for no good reason you want to impart, you drank 2 liters of fluid, 2 liters of pure water. Okay. You didn't run while I sweat or nothing. You said, I want to drink 2 liters of water. Where is that going to go? To the extracellular fluid compartment. It's not going to go to your inside of your cells, right? What's going to happen to the concentration of water in the extracellular fluid compartment? Increase. So some of that water will move into your intracellular space. What was your question?
I was just going to say that was regulated by aquaporins on some of it.
Performance, we don't worry about that. We'll worry about it later on. But what you need to know is the cell membrane is highly permeable to water. Yes, it can be aquaporins, but the cell membrane is permeable to water. It has proteins where water goes across the cell membrane. Okay, so we understand this idea. Let's say you drank water that is quite salty. That's going to go to your extracellular fluid compartment, right? What's going to happen to the concentration of water in your extracellular fluid compartment? Decrease, right?
Why decrease?
Yes, and I'm adding a lot more solute than water. It's very salty. Okay? So therefore water will leave from inside the cells to the outside. And now the concentration of water
Depend on the
inside the cells
size.
is higher than it is outside. We will give some examples of that inshallah in the next hour. And again, keep in mind, even though we're saying the cell membrane is only permeable to water, but you need to remember there is also something called metabolic pump, which is sodium potassium ATPase. We took that with the action potential, whereby you move 3 sodiums out and 2 potassiums in. But this is primary active transport. You're spending energy to do that, unlike osmosis, which is free. Okay, that's just diffusion. You don't spend energy to do that. Okay, now osmotic pressure, what is that? Well, the exact amount of pressure required to stop osmosis is called osmotic pressure. Okay, well, we will understand it a lot better if you have a U-tube like this. Not U-tube, the other one, this is the one we use in chemistry labs, a U-tube. And you have a semi-permeable membrane in the middle. I put pure water here, and I put a solution of something here, glucose or sodium here, but it's not pure water. So now let me ask you a very tricky question here. Where is the concentration of water higher, here or there? Right or left? Right. Are you sure?
Right.
It's both equal.
Pure water, what's
the
the
same.
concentration of pure water in
100.
the concentration of water in pure water?
100.
100%. Can you go above that?
No.
No, this has some stuff in it, so it certainly is not 100%. I don't need to know how much stuff it is. So therefore, the movement of water will be from here to here. But this is not going to continue until you have nothing here. You know why? Because as water moves, this side of the U-tube starts going up. And this starts going down, and the water is moving from here to there. So now, I have an amount of fluid that is that much on this side of the tube, higher than the one I have on this side. And if you take the pressure right here, see that? This is, take a horizontal line. The pressure right here is equal to the height times the density of this fluid. And this is the osmotic pressure that will stop further osmosis. Okay? Now, when I'm talking about net movement of water, there will be no net movement of water anymore from here to there. Why? Because this concentration difference is now counterbalanced by this pressure, which is called the osmotic pressure. It's the pressure that stops osmosis. Okay, now let's say I increased the concentration of this substance on this side. I increased the osmolality. Will I have more water going to this side or less?
Yes. More.
Of course I'll have more. And the diffusion is directly proportional to the difference in concentration.
Osmotic pressure
Okay.
increase.
So you can see that the osmotic pressure
Will increase.
becomes higher as I increase the osmolality in the left side of the membrane. Is that clear to everybody? This is called the osmotic pressure. So it's the pressure that is required to stop osmosis. Very simple. Now, how somebody asked about osmolality. Osmolality, this is the definition of osmolality, is osmoles per kilogram of water. Now, in our body, do I have pure water anywhere in my body? No, so therefore it's very hard to measure kilogram of water, but I can measure liter of water, and I have the osmolarity this is with an R, this is L, this is R. Osmolarity is equal osmoles over liter of water. I can measure liter of water without any problem. So therefore, you will always hear people when I see in books, they're talking about osmolality, but they really mean osmolarity. Somebody doesn't want to say osmolarity, R is difficult to say for some people. So we are talking about osmolarity, but we really mean osmolarity. But we don't care, like the difference is only 1%. In medicine, 1% is not significant. Yes, sir.
What is the difference between mole and osmole?
More, I don't know. I'll show you the next slide. You probably can determine. No chemistry.
The previous slide, so when we have no net movement,
Yes.
does that mean that the water amounts on both sides are equal?
Yes. Now I might have some water. Remember, diffusion doesn't stop, except when you have zero. You know, if you have absolute, absolute zero temperature.
ما كمية
That's when
متساوية بين
diffusion
الطرفين.
stops. But
No.
if there is no net movement, that means there is movement in both directions, but they're equal. Okay, now let's determine what is osmosis. It's the movement of water, right? Now, the osmotic pressure exerted by particles in a solution. Now we're getting to the mole and osmol. It depends, it's determined by the number of particles. Remember when we talked about the partial pressure of oxygen or partial pressure of CO2? What determined the partial pressure? And if I say gas, air in the alveoli has a high PO2, does that mean I have a higher concentration of PO2? Yes. When I say the venous blood has high PCO2, does that mean there is more concentration of CO2? Yes, that means I have more particles of CO2. So therefore, because of the movement of particles is really what determines this osmotic pressure. Okay? Remember, pressure is a force per unit area. So if I have a lot of particles, they're hitting a membrane, they're going to cause pressure. Now, this pressure is determined by the kinetic energy. And the kinetic energy is defined by mass times velocity over 2. Well, now if I have a particle that has a high mass, is it going to have high velocity? No, it's big, the velocity is low. But I'll have a certain kinetic energy. But let's take the opposite of that. If I have a particle with a small mass, do you expect it to have a higher velocity? Yes, so therefore the kinetic energy practically remains the same.
Yes.
So whether a substance, whether a particle is large or small, here we're talking about osmotic pressure. The osmotic pressure will be determined by the number of particles rather than the size of the particle. Okay? And that's why when we say we increase PCO2, I increase the number of or the concentration of CO2 in blood or in air. Okay, well, osmolarity, let's go back. Somebody asked about the osmol. Shabdil asked about the osmol. Let's define the osmol. It's 1 osmol is 1 gram molecular weight of an osmotically active solute. Did you understand any of that? I didn't either. So let's not worry about it. I'll tell you how to determine the osmols, a very easy way. What's the molecular weight of glucose? 180 grams, right? I get 180 grams of glucose. I put them in 1 liter of pure water. I'll get a solution with an osmolarity of 1 osmol. 1 osmol is equal 1,000 milliosmoles. Why did I do that? We will see in a minute. Let's take another example. What's the molecular weight of sodium chloride? 58.5. If I get 58.5 grams of sodium chloride, I put them in 1 liter of water, pure water. I'll get a solution with an osmolarity of 2 osmoles per liter. Why 2 osmoles? Because sodium chloride will dissociate into sodium and chloride. So now, instead of having 1 particle, I have 2 particles. And remember, the osmotic pressure is determined by the number of particles, not by the size of the particle. So therefore, if I take 58.5 grams of sodium chloride, put them in 1 liter of water, I'll get a solution of osmolality of 2 osmoles per liter. That's 2,000 milliosmoles per liter. Question? Well, Robin, you have a question?
Sure. In that case, it means when we put 1 mole of the substance into 1 liter of water, then that's 1 osmole?
If it doesn't dissociate.
Okay.
Okay, so now remember, our osmolarity is about 300 milliosmoles per liter. يعني تقريبا 1/3 of this. 1/3 of the glucose and 1/6 of the sodium chloride. So remember now, we find out also, remember this osmotic pressure we were talking about a minute ago? Again, we like to get numbers in medicine. We find out that the osmotic pressure that can be generated, if you have a YouTube like the one I showed you, if you have 2 solutions on each side of these, of the semi-permeable membrane, if there is a difference of 1 milliosmol between these 2 solutions, then the osmotic pressure that you will require to stop osmosis is 19.3 millimeters of mercury. Again, how do you know that? Somebody went and did an experiment and found out that this is 19.3, and it's not a very remarkable number. So try to understand this a little bit. What's the osmolarity of pure water? 0, right? Let's say the osmolarity on this side is 100 milliosmoles. So I have 0 here, 100 milliosmoles there. What is the osmotic pressure I need to get in order to stop osmosis? It will be 100 times 19.3, which is equal to 1930 millimeters of mercury. So if the osmolarity on this side was 100, the osmolarity on this side was 0, this amount of pressure that is generated by this amount of fluid would be 1930 millimeters of mercury. And now let's take an example that's closer to reality. You know our red blood cells? What's the osmolarity inside the red blood cell? 300 milliosmoles per liter? It's intracellular fluid, right? If you put that in pure water, which has 0 osmolarity, is water going to enter the cell or leave the cell? Enter the cell. As water enters the cell, what's going to happen to the pressure inside the cell? It will increase. And if you put it in pure water with osmolarity of 0, inside the osmolarity is 300. Multiply 300 by 19.3. The pressure that you will generate inside the cell is 5443 millimeters of mercury. That's why these cells will rupture. If you put any cells in pure water, they will rupture before they get to that pressure. And they cannot handle this kind of pressure. Your blood pressure is 120/80. This is 5,443. The cell will rupture way before you get to that point. Okay, now the osmolarity of the, of our body fluids is equal everywhere. Here I'm telling you it's 282, it's not 300, it's okay. Any number between 280 and 300 is fine. We will define an osmolarity of 282 milliosmoles per liter as isotonic. Anything above that, we call it hypertonic. Anything below that, we call it hypotonic. Now, examples of isotonic solutions, 0.9 sodium chloride and 5% solution of glucose. Remember, if you visit your friend while you go to the hospital, you find these bags hanging over people's heads. If you go and read what's written on them, chances are there's 0.9 sodium chloride, while 5% glucose. And very often we give people isotonic solutions, especially if they're dehydrated. But of course, in some cases, you might have to give them hypertonic or hypotonic solutions. Now, this is a cell, right? If I put that cell in an isotonic solution with an osmolarity of 280, is the size of that cell going to change? No. If I put it in hypotonic solution, is it going to increase in size or get reduced in size? It will increase and the water will move to the inside of the cell. How about if I put it in hypertonic solution? It will shrink and it will lose a lot of water from inside of that cell. Okay, well let me stop here. Inshallah, we'll see you tomorrow, except if you have any questions.